I am Professor Collins, and this is your daily dose of statistics. Today we're going to be talking about bivariate statistics, and specifically we will be looking at analysis with the interval/ratio variables. Which means that we'll be talking about the interval ratio associations, and specifically regression analysis and correlation using the Pearson's R statistic. So first let's talk about regression analysis. Now regression analysis obviously uses continuous interval ratio variables, and the purpose of regression analysis is to predict scores on the variable y based on your variable x, based on scores of your variable x. And what it does is regression estimates the effect of x on y, so how much your scores on x affect the scores on variable y, the effect strength, and the direction of the effect. So let's do a quick little running example looking at Skid Row.
I was living on the 6th floor of a loft building on 6th Street in San Pedro in Skid Row. It's sort of ground zero. Skid Row is basically a 50-block area of downtown Los Angeles between 2nd and 7th Streets and Main and Central Streets, with 9,000 people in varied states of homelessness. Psych patients, crack addicts, heroin addicts, soccer moms and gangsters, artists, Agent Orange vets, the missions, the welfare hotels, the real estate investors, the parolees, the dealers, the sex offenders, and the issues. Housing, racism, employment, addiction, mental health. There's a lot going on in 50 square blocks. I wrote a series of cover stories for the LA Weekly. LAPD Police Chief Bratton told me it was the worst social disaster in America. The U.S. Department of Housing and Urban Development's definition of homelessness includes a person who has no place to go, no resources to obtain housing, and is either being evicted within a week, discharged within a week from an institution such as a hospital, or is fleeing domestic violence. The average age of a homeless person living in the U.S. is 9 years old, 3.5 million people. That's 1.35 million children. In LA County, 80,000 homeless each night. Los Angeles is the first third world city in the United States. Some people are here to take advantage of the centralized services, the huge homeless mega shelter missions who provide meals, emergency shelter, showers, haircuts and shaves, mail delivery, legal assistance, 12-step recovery programs, medical, dental, housing placement assistance, and social service liaison. Skid Row is home to other populations as well. An undercover criminal sect hiding out, and a predatory population selling drugs and preying upon legitimate residents. I've been in the streets and the missions, and I knew people's names and their faces. I was watching the madness play itself out in the streets from my window. I started shooting some video from a little handy cam. That was the view from up here. The streets and discovered that what was a frightening sight from a moving car was actually a community of people. So what is it that makes Los Angeles Skid Row unique? The scope of it and the proximity to the financial district? The 5-star hotels and the street sleepers butted right up against each other? The fact that it's predominantly black? How could all of this be happening in one of the richest economies in the country? measure of any society is how it treats its weakest element, the widows, the orphans, and the strangers in the land. How we do anything is how we do everything. We're not doing so well on Skid Row.
Okay, so let's say we're interested, so we have this problem, right? We have this problem of Skid Row and some of the issues that occur in Skid Row. And so say we're interested in running statistics and we've collected data and we're interested in answering some questions regarding Skid Row. And so let's say we have a question such as this. What is the effect of the number of social service programs in a neighborhood on the average number of homeless residents? So what that means is, so in this case, what we would be wondering, right, is if there's a relationship between the number of social service programs in a neighborhood and the number of homeless residents in those neighborhoods. So in this case, our X variable would be the number of social service programs in a particular area or in a particular neighborhood, and our Y variable would be the average number of homeless residents per night. So that would also be our continuous interval ratio variable. And so this is an important point to make that I just want to make real quick. The regression does not necessitate causation, or doesn't mean causation, because we're doing something with a regression analysis. And statistically, conceptually, with the statistics, it looks like causation. We can only have what's called theoretical causation, right? Or causation based on our theoretical framework. The statistics cannot allow us to infer causation. All we can do is infer a relationship between these two variables. And so this is one of those questions, this research question up here is one of those correlation or relationship type of questions, right? So these two variables may be associated, so we're looking at the association. So it's hard to disentangle causation from this relationship, right? So we could ask the question, do the number of homeless residents cause more programs to be established in a neighborhood, or do social service programs in a neighborhood tend to draw in residents, right? And so that's the issue here, is that this can occur one of two ways, right? So statistically what we're doing is we're looking at the relationship of the social service programs as it relates to homeless residents per night, but we're not inferring causation per se. So let's take a look at understanding trends and prediction in regression analysis. So let's say we have a number, the number of social service programs. Say we've taken data from 11 different neighborhoods in Seattle, and we're interested in the relationship between the number of social service programs in each neighborhood and the average number of homeless residents in each of those neighborhoods. And so this is what regression does, is it looks at the relationship between these two variables. So the nice thing about regression is what we can do is we can use trend lines or plots to identify the potential relationship. So what we can do is we can take something like variable x and plot it on the x-axis, and take variable y and plot it on the y-axis, and create a plot, right? Create a graph based on those data, or a dot graph, right? And then what we can go ahead and do is we can plot what's called a regression line. And what a regression line is, it's the average relationship across all of these data points, right? So the average relationship, the average linear relationship across all of these data points. And so then what we can go on and do, the nice thing about regression is what we can do is we can use this trend line and go ahead and predict other variable x's. So for example, if we're interested, if we have data for, let's say, Lake City, and we know that Lake City has, let's say, 16 social service programs, what we can do is we can use this trend line to predict the average number of homeless residents that Lake City should have, right, based on this information. So that's one of the nice things about regression analysis. So let's take a little bit into the equation for regression analysis, and we'll get into this a lot more in the next piece here. So what we can do, like I said before, is use the number on the x variable to predict the case number on the y variable, right? And so the basic equation here is y equals a plus b times x, where y is the score on the dependent variable, a is the y-intercept, which is the location where the regression line crosses or intercepts the y-axis. So in this case, this would be the number of homeless people in an average neighborhood for a neighborhood that has 0 social service programs, right? And so that's this point here, where 0 on the x-axis intersects with y. And then the slope, the b, our b here is the slope of the regression line, and that's the amount of change in in y by each unit change in x. So we've heard of this as rise over run, right? The slope of that regression line is what this is. And x is our score on the independent variable. So each of those scores on our x variable is what x is. And so we'll get into this in a little bit more detail. So let's talk about how to calculate regression.
This video is to run you through the calculations for all of the necessary components for both regression and correlation. So just a quick note, what we're going to need here is the mean of x, the mean of y, so your x variable, your y variable, x and y, and then the sum of the different score of x minus the mean of x times y minus the mean of y. Then we will also need the sum of the different score of x minus x squared, and then we'll need the same thing for the y variable. Right? So we'll need several different components for both regression and correlation. And then what we'll do is we'll plug them in later, and I'll keep them color-coded to try to keep consistent with everything. So first what we're going to need to do is find the mean of x. And so the way we do that in Excel is using the function average. Excel doesn't have a function called mean, so it just uses the average. So we'll go ahead and do that, plug that in. And then what we'll do is we'll do the same thing for y. Right? So we use, again, the average function. Click on that, open parentheses, and then we just click and drag, close the parentheses, and there we go. So we have our two means there. Now we need to get the difference between x and the mean of x, or x mean, and so we will do that by doing our equal sign here, and then we have our x, and then we, of course, minus times the mean, or not times the mean, but minus the mean, and we hit enter. And so just a note here, Excel is relational, and what that means is if I drag this down, meaning if I copy and paste this here, we will just get the 5 here, and that's because it, if we take a look here, it is highlighting the cell below the mean. So we want to keep that standard. So what we'll do is we'll remove this, and the way to keep a cell non-relational is by putting little dollar signs before the cell. So what that means is it's going to stay at B13, at cell B13. But it will still follow the other cells. So as you can see here, right, it followed this cell down, but we still have B13. So keep that in mind. We're going to need to do that for y as well. So we'll drag that down. Now we have all of the different scores. Now we'll do the same thing for y. So we'll do y minus the mean of y. And we'll want to go ahead and put our dollar signs in there to keep it non-relational for that. And we'll bring that all the way down. Now we need to do this and this cell times each other. Right? So that's what this is representing here. So we have the difference of x, the difference of y, and we will times those together. So to do that, we have our equal sign, do x, and in Excel times is the little asterisk here, times y. Bring that down, pushing enter, and then we'll just bring this all the way down. And that will gives us our difference of x times y. Now what we need to do is sum all of these. So this is not the average, this is the sum. And we'll use this in our equation later. So the way to do this is we use the sum function in Excel. And we'll go ahead and highlight that whole column, close the parentheses, and we have our sum of that equation there. Now, next step, so we've gone through, 1, 2, 3, 4 steps here. No, actually 1, 2, 3, 4, 5 different steps, 6 different steps. So now we'll be on step 7, which is taking the x difference score and squaring it. And so what we'll do is we'll find each of our x's, our x difference scores, and then we'll do times and x difference. And so just to know, Excel has a function called power. And just to show you what I mean, I'll just use it, but I'll remove it. So we can use the power function, and then the number, and then comma power 2, right? So that's basically saying to the second power, C2 to the second power, and it'll be the same thing. So we'll just remove that just to keep this. It's just easier for me to do the cell times the cell. So we'll do this, bring it all the way down, and we get our numbers, all of our numbers here. And then what we'll do is we'll sum that. So we need to take the sum of those scores. We'll sum, and we'll highlight all of those. And let's move that right. Move that right. And we will do the same thing for the difference of x's. Right? So we'll square those. And bring those all the way up. I did the wrong one, didn't I? Or did I do the right one? Let's double check just to make sure. Yep, okay, there we go. There we go. Wow, that was just a very large number. So we'll bring that all the way down. And then we'll we'll use our sum function. And so I'm going through this fairly quickly, obviously. So just take your time and be sure that you get all of the correct numbers and that you're going through all the steps for this. So here we have our 1, 2, 3, 4, 5 numbers that we'll be using to calculate both our beta as well as our R statistic for the correlation.
So now you see how to calculate each of those components. So we'll be using those 5 components to calculate our regression score, or our regression equation. And so again, here's our baseline equation: y equals a plus b times x. And so first, let's find our beta value, or our b score, right? So that's the one next to the x. And the equation for this is the sum of x minus x bar times y minus y bar, or another way to say this is the sum of the deviation scores of x times the deviation scores of y. Now, if you recall in the video that you just watched, the short little clip in Excel, we have this value, right? This value was calculated, and it is actually color-coded in green in the video. So we'll go ahead and plug this in. The same thing is with the denominator here. The denominator is the sum of the deviation of the x scores squared. And again, we have that value. It is turquoise in the video, right? So we go ahead and plug those two numbers in, and what we come up with is a total of 16.25. So our beta, or our b value here, is going to be 16.25 in our regression equation. And so we can use that and plug that in. Now let's calculate our y-intercept. Our y-intercept is, we can basically just kind of rearrange the the regression equation to come up with the y-intercept, or the a value. And so a equals the average or the mean of y minus b times the mean of x. And so we can plug these values in, right? We have our average of y, or our mean of y, which is 242.09, minus our beta value, which we just got, right, our 16.25, and times that by 12.91, which is the average or the mean of x. And what we get there is 132.27. So now our final equation is x equals 132.27 plus 16.25 times x. Now this is not one single value, right? So you're probably wondering what's the point of this total equation. So again, remember we were talking about prediction for regression. And so now what we can do is we can use this value to predict other values. So let's take a look again at our Lake City value. So let's look at all of our different our different neighborhoods, right? And so we have raw scores for each neighborhood. These raw scores is what helped us identify and create our regression equation. And so now what we can do is we can predict the value for Lake City, right? So we can predict, based on the number of social service programs in Lake City, we can predict what should be the number of residents, the average number of residents per night in Lake City, using this equation. So we have y equals 132.27, right? That's our intercept. So that what that means is that when there are no when there are no social service programs in the neighborhood, a neighborhood should have about 132.27 homeless residents in that neighborhood. Plus 16.25, which is our slope, times x. And so what we do here is we plug in x for Lake City. And this will help us identify what our y in Lake City would be. So if we solve this equation, we're going to get 392.33. So based on the data that we have, what this is telling us that Lake City should, given that it has 16 social service programs, Lake City should have 392.33 homeless residents in Lake City. Right, so now we know how to calculate regression. Now let's take a look at correlation, right? So these two are highly related to each other. So we'll jump over and take a look at correlation and the use of correlation with regard to regression. And so what do we use correlation for? Well, again, correlation utilizes continuous and interval ratios, just like regression. It's used to understand the association between y and x variables. And again, it analyzes, just like regression, the relationship between the variables, relationship strength, and relationship direction. And correlation, unlike regression, varies between 0 and 1. So we can use this, as we've seen with other measures of association, we can use this to identify the strength of relationship and the actual variance accounted for in y based on the value of x. And so our basic research question for correlation is, how strong is the relationship between x and y? So again, let's take a look at our data. So we have our data up here on the right, our raw data. And so we're looking at the relationship between x and y, or the relationship between number of social service programs in a neighborhood and average number of homeless residents. And so as you can see, here's our basic Pearson-R's correlation equation, right? Our Pearson-R equation. And so we have this value again, the sum of the x deviation scores times the y deviation scores, divided by the square root of the sum of the x deviation scores squared times the sum of the y deviation scores squared, right? And so what we can do, again, using that data that we calculated in Excel, we can plug in our numbers. And so as you can see, the sum of the y deviation scores squared is very large. That will come down because we're taking the square root of those, right? And so we can plug in our numbers, or we can calculate the denominator here. So we've done that. And what we come up with is a R correlation value of 0.79. So we can use that value to look at how strong the association is. So we can use this chart as you've seen before. And what we find is that our association is strong. And so the nice thing about correlation is it actually goes beyond this, right? We can do more with correlation than just this. We can actually look at the percent of total variance accounted for in our y-scores based on x. And so how we do that is we use our r squared. So all we do is we simply square our r value, right? So we take 0.79, as we found in our r value, and we square that, and what we come up with is 0.636. And so what this tells us, or 63.6% if we want to change it to percentage. And so what this tells us is if we have our little Venn diagram here, and we have homelessness in blue, and we have service programs, what this is telling us is that service programs account for 63.6% of the of the total variation in homelessness in each neighborhood, right? And so this accounts for 63% or 63.6% of homelessness in neighborhoods based on the number of social service programs in those neighborhoods. And so now we can take this information and we can use it and plug in the numbers to identify whether or not this is a significant relationship, right? So all of this regression and correlation is accumulating to identify whether or not there isn't actually a significant relationship here. And so we'll go through our 5-step model. Step number 1 is making assumptions and meeting test requirements. And so our assumptions for correlation and regression are that the sampling is random, the sampling distribution is normal, the level of measurement is interval ratio, we have bivariate normal distributions, so each variable is normally distributed, and there's a linear relationship. And so what that means is basically as x increases or decreases, y at a fairly equal rate increases and decreases, increases or decreases at about the same rate. Step 2, we need to state our null and research hypotheses. So this is fairly basic for correlation. All we're doing is saying that for our null hypothesis, that our probability is 0, equals 0, right? So essentially what this is saying is there is no relationship between the two variables. So the relationship is 0, there is none. Whereas our research hypothesis is that there is a relationship between the two variables. So it does not equal 0, there is some relationship there. So now we'll go to our critical region. And so we use our sampling distribution of the t-distribution at the alpha level of 0.05. And so this alpha level is important, right? We know this, we've talked about it a lot. It's going to come up in a few minutes, so just kind of keep this in the back of your mind. And another note too, our alpha level is the alpha level of our sampling distribution, right? So we're looking at a 0.05 of our sampling distribution. Degrees of freedom is measured by n minus 2, or sample size minus 2. In this case, we have a sample size of 11. So we have 11 different neighborhoods, right? 11 different cases. And so we have 11 by minus 2, which equals 9. And so what we'll do is we'll use that degrees of freedom, and we'll look at our t-test table, and we'll identify where in our t-table our critical value is. And so we have our degrees of freedom here, and we have a degrees of freedom of 9. And we're looking at a two-tailed test, so correlation is always going to be a two-tailed test. And we have our critical region of 2.262. And so what we can do is we can plot that onto our normal distribution. And so we're looking at plus or minus 2.262. And so that is our t critical region, right? So when we're calculating our t observed value, we're trying to identify whether or not the value is beyond that region or within those tails. So now step 4, what we need to do is compute the test statistic. And so our test statistic here is calculated with this equation, or a t obtained value. And what we have here is r times the square root of n minus 2 divided by 1 minus r squared. And so we have all of these data, right? We have both our r and our r squared, and we can plug these in. And so our r value is 0.79, as we calculated earlier, and our r squared is 0.636, as we calculated earlier, and we can plug in these data. And what we get is 0.79 times the square root of 24.71. We calculate that out, and our final value is 3.96. And so what that tells us is, if we plot this next to our critical region, what we find is it is indeed in the tails. And so what we can do here is we can move on using this information and make some assumptions about the data and interpret what we found. And so we need to make a decision here. So we found that we have our two hypotheses here, our null and research hypothesis. And we found that because our obtained value was larger than our critical value, we can reject the null hypothesis, right? So what we're saying here is that there is a relationship between our two variables. There is a significant relationship between our two variables. And so we can interpret that, right? What we can say is there's a positive and significant relationship between the number of social services present in a neighborhood and average number of homeless residents in those neighborhoods. And also what's important, just to make a note here, going back to correlation a little bit, the R value can be positive or negative, right? So we're looking for a positive or negative relationship in this case. Negative relationship means that there is a negative relationship, right? Which going back means that as one value increases, the other value decreases, right? Whereas a positive relationship means that both values increase at the same time. So now we've gone over correlation. Now let's look at how to actually use this in SPSS and relate this information that we just calculated to SPSS and what it actually looks like in SPSS.
Full view. So you can see our three variables: neighborhood, programs, and homeless. And so these just
restart this.
I'm quickly going to run you through running a regression analysis with our data here. And so let's take a look at the variable view. So you can see our three variables: neighborhood, programs, and homeless. And so these describe which neighborhood, the number of social service programs within each neighborhood, and the average number of homeless residents within each neighborhood. And as you can see, the first is nominal, and that is really more an identifier, so to identify which neighborhood, and you can see the names when we click back over to data view. And our two variables of interest, our x variable is scale, and so that's interval ratio. Same thing with our y variable, and both are interval ratio. So let's head back over to data view, check this out. So as you can see, we have each neighborhood and the number of programs and homeless, average homeless residents within each, right? So our question here is, are the number of programs and the number of homeless, average number of homeless people within each neighborhood related? And so what we'll do here is we'll go to regression, so analyze, regression, and then linear. So I'm going to go through this fairly quickly, so if you need to back it up, slow it down, pause it, go ahead and do that. So in our dependent variable, that's going to be our y variable. We're looking at the average number of homeless residents, right? So we'll put that in the dependent variable. And then our x variable is the number of social service programs. So we'll put that there into the independent variable, right? So those are interchangeable. X and independent and y and dependent are the same thing. So now we want to click on our statistics. So what we want is our model fit. And then we want our descriptives. So those are the two boxes that you'll want to click. Our model fit gives us our R squared and our R values, and then the descriptives will give us our correlations and our means and standard deviations for each variable. So we'll click on continue and click OK, and our little box will come up here. And so as you can see, we have our descriptive statistics at the top, so our mean for each of our variables, average number of homeless people, number of social service programs, and then we have our correlation matrix right here. And so this is our correlation, this is our significance, and this is our sample size. And then we have our model statistics, our R squared. This ANOVA box, we'll actually just ignore that for now. That's going to be important when we get into multiple regression, but for now it's not important. And then we have our coefficients, which we'll get into in a moment.
So now you've seen how to compute regression and correlation in SPSS. Now let's just take a look at our data and what we have and compare that to what SPSS outputs. And so here's our data, right? So we have our mean of x, our mean of y, we have our slope, we have our y-intercept, we have our regression equation, which is predictive, so this won't actually show up in the SPSS output. We have our correlation coefficient. We have what's called our coefficient of determination, or an easier way to put it is just our R squared. And that's kind of a standard term, so if you just say R squared, most statisticians will know what you're talking about. And our obtained t-value. And again, just remember, while I don't have this on here, our alpha level is 0.05, right? And so we're looking for a significance level that is less than 0.05, meaning the extent to which this occurs by chance is less than 5%. So let's just take a look at some of this output. So our first little box that we have in our output are our descriptive statistics. So for this, we'll find our mean of y and our mean of x. And so I'm doing a little rounding here, so you can kind of see that. Then we will have our correlation matrix. And so you can see in the correlation matrix, we have our Pearson correlation. And then we also have our significance for the one-tailed test in the correlation as well. So we can just ignore that. We ran that earlier, and we'll see that again. The significance level, we'll see that again. And then in our model summary, we'll find our correlation coefficient, or our R value, right? And so you'll see here it's big R for some reason. I honestly don't know why SPSS outputs it as a large R. The standard is a small r. Just keep that in mind. And so our R value, 0.797, and our R squared, 0.636, right? So our coefficient of determination. So you're seeing all of these things pop up, right? And now let's take a look at our coefficients. And so this will tell us both our slope and our y-intercept, and it'll let us know whether or not the relationship between our independent variable, our x variable, number of programs, and our dependent variable, or average number of homeless residents, is related, right? And so here's our y-intercept, right? So this is our b constant. And so this can be a little confusing because it looks like a beta, right? Like a b, but it's in fact our a value. So when you see the b constant under unstandardized coefficients, that is the y-intercept. And it's sort of interesting, programs like Excel, for example, will actually say intercept value, and other programs will as well. SPSS calls this the constant. So just note that this is your y-intercept. And then your slope is right below it. It's 16.25, right? 16.254 as SPSS outputs. So that's identifying that information. And then we have our t-value, right? So that's our obtained t-value. So this is the value for this variable, right? Relating this one specific variable to the outcome variable or the dependent variable. Now this variable, so it's this attained value that SPSS is relating against the critical t value. And what it's saying is that this value, looking at the significance level right here, this value is significantly greater than the obtained, or excuse me, than the critical value, right? But SPSS doesn't actually show the critical value, so that's important to note. So now that we have all this data, right, we can make the assumption that we can accept our null, or excuse me, our research hypothesis that there is a relationship between the average, or the number of social programs in a neighborhood and the average number of homeless residents. And regression, what we would say is that in this case, the number of, even though, so again, note that we can't necessarily infer causality, what we're saying here is that the number of social service programs predicts the number of homeless residents in a particular neighborhood. So that is our lesson on interval ratio associations. And that concludes our whole session on bivariate associations. And so we will be moving on from bivariate statistics up to multivariate statistics next. And we will be near the top of our mountain in our next session. So this has been your daily dose of statistics. Thanks for listening.